No, we didn't. Maybe we did. I doubt it. So I'll look up Hamming code, and if I don't put it up, please send me an email just to remind me to dig out. If not, I'll record something very quickly. Okay, so we're finished with Hamming code. And listen, the error detection system is a definite exam question. So make sure you're okay with parity, block parity, Hamming code, and now we're going to do CRC, and then finally we'll do the checksum system. So, and by the way, again, before I forget, and this is recorded, we missed on the bank holiday last Monday, so we're going to make it up next Monday. So there will be a class next Monday. I can see something.
Why was there going to be no class? What do you mean? I thought there was always...
We will have a replacement class on Monday. See, last Monday, you weren't here, right?
What do you mean replacement? I thought we had a class anyways, no?
Did we have a class? No, we did not.
I mean,
No, we had a bank holiday. There was a bank holiday Monday, last Monday.
Yeah.
So we did not have a class.
Yeah.
And we need to have a lecture, a night, where an evening where you come in and you get another lecture as a replacement for the missing Monday.
So what do you mean?
I mean, if you come over here next Monday and you sit here, well, if the room is changed, I'll send you an email, but if it's the same room, we'll meet next Monday as well.
Yeah. We're not supposed to.
No, oh, no. Next Monday is an assignment. Next week is an assignment week. There are no lectures.
Oh.
So for that.
I didn't know, sorry. Yeah.
Okay, you didn't know that.
That's what I was saying, yeah.
Okay. All right. Next week, there are no lectures generally unless pre-planned, as this is what I am now pre-planning for you to come in next Monday, please. And we missed a couple of some of the topics that we need to cover. And if you don't come up, I'll record it, unless if I forget recording. Okay. So let me close this and. Yeah, every semester there are 6. A semester consists of 12 weeks with 1 week in between.
Yeah.
Week 7 is called assignment week. No lectures, but don't book any holidays. There'll be assignment.
I thought it was called reading week in DCU, but commuting students never got it. So I just assumed it was the same here. We never got it.
Where was that?
DCU. Like I think it was computing and one other course, business. Yeah, they didn't give the break.
No. We give you the break here. But when we give you the break, we give you work to do during that break.
Yeah. Well,
we give you all the assignments. Anyway, don't worry about it.
Do you remember saying we have class tests? Like, is there a contingency test?
There was a tutorial. I hope you did it.
Tutorial, yeah.
Yeah, well, tutorials. And next Monday, like I'll give you a tutorial tonight as well. So that's tutorial 2. Yeah. Then on Monday, when you come over, I give you an assignment that you'll have 2 weeks to do. And then when you come back, there'll be 3 more tutorials and 1 test.
Like a class test or the actual test?
No, a test, a class test. And that's what makes your course work.
Yeah.
And then 1 final exam, that's a separate thing. You need to pass that separate to the coursework. I thought I explained that on the first lecture. Yeah, don't worry. All right, so what am I going to talk about now? Hopefully it's going to switch to. Now, I don't know if the recording will actually work here. I hope so. Right, we're going to do something called CRC Error Detection System. And CRC stands for Cyclic Redundancy Check. It's a protocol, so it stands CRC, that's what it's called. And CRC is an error detection system. It's probably the best and most commonly used error detection system in communication networks today. It discovers more errors than any other error detection system, and it's extremely fast as well. So, but speed is not its advantage because most of the others are fast. Anything that works by, like parity, they're all logical operation kind of programs. And this has also very little redundant data attached to a frame. This is the way it works. First, let me give you the basic idea of CRC, and then we'll get to talk about the details, just like with the Hamming code earlier on. The basic idea in CRC is, for example, if I give you a message that consists of numbers, just imagine, it's not exactly like this, but it's just to give you the overall, what it might appear like. Let's say I give you the number 33 plus 12 plus 7 plus 20. I don't know, what's the sum of these numbers now? That's 55, 64, 71, and let's say another 14. So that makes 85 altogether. For example, you sum all these up and they're 85. That's the sender. And let's say you and I agree on, I'll send you another number that will complement all this to 100, just for argument's sake, right? So that's what I'll send. So what's the idea is that what I'll give you here that will complement all these numbers to 100. So if you were the receiver now, receive this frame, remember 15 is not part of the data. It's an extra redundant data sent by the sender. So now, if the receiver receives this frame, it will start saying 33 plus 12, that's 45, that's 52, 72. Oh,
It's 86.
so it's 86, is it?
Yeah.
I knew it. I don't know. Okay, maybe, I think this was meant to be a 13. This was a 13. So 33, 46, 52, 72, 72, and 13. That's 85. So now that's all, maybe it's 85. I just assume it's 85. Plus 15 is 100. So I'm happy, we're happy. The receiver is happy. Because if something changed, if this 7 turned into a 6, when the receiver adds all these up, there'll be 99. They won't make up 100. So that's really the basic idea. But this is on decimal numbers. And in decimal numbers, we add them. Your computers are a little bit slow at adding, so we use something similar, something different to adding or division or whatever. And then as it divides it, like the number gets bigger, as it divides it by 100 or whatever, there's division. And then working out the complement can be slow in decimal numbers. In binary, it's so fast. So let's see how does a computer do a CRC? How does CRC happen? Now, first, CRC did I get this right? That could be the summing number. No, okay. Let me rephrase this. No, it's recorded. Let me rephrase it slightly different. So you take all these numbers and we say, divide them. Let's say they all added up to 85. And let's say I give you a number. This is really bad example, sorry guys. Okay, let's say I want to divide them by 10. Let's say we both agree on a divisor. That's not, I don't give you the sum. I add them up and I divide them by 10. What's that? 8 and a bit is a remainder. There is fractions are remained. What would complement this number to divide by 10 without a remainder? That's exactly what CRC, the idea. So I go for all these, divide them by 10, and find out, does it divide by 10 without any remainder? And if it doesn't, what would take to this number, how would I complement it to the nearest complement to make sure it divides without a remainder? And in this case, I'd say 5. So that's what I add 5 here. So 5 here is the complement to all these numbers. So if you divide them by some given divider, divisor, the remainder will be 0. So now if the receiver receives all these, 85 and 5 is 90, so when it divides 90 divided by 10, it's 9 without any remainder and says it's good. But if this 12, if this 13 turned into 14, then when it adds them up, it'll be 86 plus 5, that's 91, divided by 10 is 9.1, so there is a remainder that knows there is an error. Right? This is the closer way to CRC. So how does it happen? So the sender and the receiver must agree on a divisor. What's that number that we'll be dividing on? It's not a key, it's not a secretive, it's a divisor that works and gives a good remainder. So best way is to have an example. Let's say we have the following example, 11000111. Here's the data that we want to send, and we want to act as a sender and as a receiver. We want to see if we can improve this or send this data. So we'll see what the sender does and what the receiver does. Let me get ahead. I have the steps written here for the sender. Just saves me writing them down for you, so it saves time, but it looks like it's going to be faster writing it down. And then we have the receiver. So this is what the sender does. These are the steps involved. Identify the data. So once you're given the data to send, first make sure you have your data. That's the data. The next thing, identify the generator. This is the divisor that agreed between sender and receiver. And let's say it's 1011. It's measured, this is the number that we will be dividing by. Okay, so that's the divisor that's both the generator, the sender and the receiver agree. That number, whatever that number is, that's 4 and 3, 7, number 7, but doesn't matter, it's in binary. So that's it, step number 1, done. We know our data. Of course, the data can be 4,000 bytes frame, but we're gonna use it on a short data. The next thing, append zeros to the end of your data. How many zeros? One less than the length of the generator. The length, not the value. How many bits is the generator? It's 4 bits in this case. So we're gonna append 3 zeros to the data. So this 0, 0, and 0. Now that's an important step, and that's a different step, and it's only done by the sender. The receiver doesn't do that. Right, start the division. Divide all your data divided by the generator that we call the generator. And it's long division. But computers, obviously, division will be very slow. So it doesn't divide. It actually does something called XORing. You know what XOR is? Do you remember? ORing, I don't know if you remember ORing. Remember the OR table. If the OR table, just to remind you what the OR table looks like. If you have 2 values, X and Y, what is X or Y, the result? If X is 0 and Y is 0, what's X or Y? A 0, you know. It's like having 2 switches. You have switch A or switch B. And there's a lamp here, and there's a battery here. So if both of them are 0, both switches are open. Oh, sorry. If switch A is open and switch B is open, that's 0 and 0, the light will not go on. if switch A is closed or B closed, so for the A, that's X and Y, that's what I meant by A and B. So if one of the switches closes, then the light will come on. And if the first switch closes and the second one is open, the light will come on. What if the two of them are closed? If X close and Y close, of course the light will come on as well. That's if it was OR. But now we're talking about exclusive OR. It's exclusive, but they write it XOR. So the XOR, that means you can't have the two of them on. Only one of them is on, the light will come on. But if the two of them is on, the light will not come on. That's what exclusive OR means. So just remember this table. I'll write it down again later on. So how do we do this? Let's divide. First, divide. I don't know if you remember the old division. I'll remind you, I'll do it for you. I had a black pen. Black seems to write clearer. But it doesn't. I don't have it with me. So let's carry on with the blue one. Right. To divide, and this is something you need to do. This is how you should do it. We're not interested in the result that come out at the top. We're just interested in how the process continues. So this is the way to continue, guys. You take the divisor and you put it underneath the data. 1, 0, 1, 1. This is how you divide. Imagine the result, of course, is going to be 1 or 0 at the top. If it's 1, you multiply into that, and this comes as is. Now, and normally in division, we subtract or add, subtract these. What's the difference between them? But now that's where we XOR, where the XOR comes in. So that XORed with that. So 0 XORed with 1 is 0. 0 XORed with 1 is 0. 1 XORed with 0 is 0. But when the two of them are on, sorry. I was testing you guys. Yeah. Wow, yeah. Yeah, and you're falling asleep on me. So that's 1, 1, 1, right? And then when the two of them are ones, the result is 0. Okay, here's the table, just in case you start forgetting. It's too big to show. So I'll just do it here. 0, 0, 0. 0, 1, 1, 1, 0, 1, and 1, 1, 0. Here's the XOR table. So 0, 1, 0, 1, that's it. The results are 1. 1, 0 is 1. And when the two of them are 1, 0. Now, good idea to cross any zeros on the left, because they get you mixed up. Right. Now, don't divide unless you have the same number of bits. This one has 4 bits. You can't divide a small number that only has 3 bits. So this is where you bring down as many bits as you need. So we only need 1 bit. So we bring the 1 down. Now we have 4 ones divided by this one, and you do the same thing. All you have to do is bring down the next, the same generator. That's 1, 0, 1, 1. Just put them in the right position. And, right, what's XOR? That XOR with that. Do you want to give me the result?
0, 1, 0, 0.
Perfect. And don't forget, cross over the 0 on the left. So we have 3 bits. How many bits do we need to bring down? 1, right? And have an arrow bringing it down, because later on you could bring a bit twice, and that can give you completely different results. Be careful. It's very important to just bring exactly the same bits. Right, and then we do the same thing. So it's so easy. That's why it's repetitive. That's why this is called cyclic. It starts at the start of the frame, it goes cycling until it reaches the end. So fast, unbelievable speed. Right, so then we go 1, 0, 1, 1. Right, and what's the XOR for this now? It's your turn.
0, 1.
Starting from the left.
Oh, sorry, 0, 0, 1, 0.
1, 0. And what do we do with the 2 zeros on the left? Cross them out. Now, how many bits do I need to bring down? 2 bits. We'll bring down the 1 and the 0. Now, I'm going to bring down the next bit here, which is the next generator, so 1011. Now, do you want to give me the XOR operation here, result?
0, 0, 0.
Perfect. Right, how many bits do I need to bring down? 3, right? But there are only 2 zeros. That's it. If you don't have any more bits, then you finished. So that's the remainder. That's like, remember earlier on, we divide 85 by 10, you got 8 or something, but there is a remainder. Now, in the decimal, we looked for the complement of that remainder. Now, in binary, it's the same complement. You don't have to change it. So that's the complement that goes at the end of the frame. So what is our original frame? 110011 without the 3 zeros. Now we're going to replace the 3 zeros with those bits that are called the CRC, or the frame check sequence. So that's 100. If, for example, if this result was 001, how many bits do you take? You must take 4 bits. This is wrong, actually. I only had, no, so yeah. So you must take 1 less than the length of the generator. Same as the number of zeros. We had 3 zeros, because why did we only pick 3 zeros? Because it's 4 minus 1. Same here. For example, just for example, guys, if the result here was 001, 0001, what bits do you take? You must take 3 bits. Feed in zeros if you have to. So you would have taken 001 instead, but for now, I don't want to mix you up. So you take whatever 3 bits from the right-hand side. Now it happens to be this one. So that's how CRC, how the sender would work. Now, I just want to left the last instruction for the sender. These are the sender instructions. Identify your data. We identified our data and our generator. Append zeros. We put in 3 zeros on the right-hand side of the data at the end of the data. Divide. In fact, it's not division, it's XORing, which is extremely fast operation as well. Now, when you finish, the remainder is appended to the data. So now we took this remainder, which is 100, and we appended it to the data. But be careful, if the remainder was 010, you know, 00010, only 1 0, you don't append 2 bits, you must append 3 bits. So this is the frame that we send. Pardon?
The remainder 0.
You put them as they are, 3 zeros. You always must send that amount. So now let's act as a receiver, and let's imagine we receive this frame. This is the frame we received. So I'm gonna put it down there, and we'll see what does the receiver do, and we'll imagine if it has an error, and we'll see how it works. So this is the frame that was sent by the sender. And if we'll assume there's nothing wrong with it, and then later on we'll flip 1 or 2 of the bits and we see if we can discover them. So now we're going to act as the receivers. So there's a slight difference between a sender and a receiver. And here's the actual instructions for the receiver. So they are on the slides, actually. They're on the PowerPoint slides. So you don't have to write them, but okay. So if you are a receiver, first identify the data, which same as the sender. Identify the generator, which is the divisor, which I can't remember what it was, but I think it's 1101. And identify your frame check sequence, or CRC. So that's 2 names for it. Some books, they call it the frame check sequence. That's the sequence that's used to check the frame for errors. That's the general name. But those that use CRC, they just call it CRC. That's the CRC we're sending out. In fact, in the protocol, when they describe the frame, that field is called the CRC field. Some protocols, they call it frame check sequence field. But okay, so now let's say if we didn't know, let's say you don't know, you just received a frame, and you were told, I don't know, what was that? What was the generator we used? 1011. So we use 1011 is our generator, and the data we received is 1100111100. So that's the frame we received. And this is the agreed generator, the agreed number that we use as a divisor. Now, where is the frame check sequence? How do you know which part of the frame is the frame check sequence? The CRC that was generated by the sender and sent at the end of the frame. This is the end of the frame, we know that. But how do you know how many bits of these are the data? Or what's the data? And is it 2 bits or 4 bits? It could be 7 bits. How do you know which?
1 minus the 5.
Yeah, once you know what the generator is, it's 1 less than the length of the generator. So if the generator is 4 bits, then the last 3 bits. What if the generator is 14 bits? Then the last 13 bits here are.
Is that really message or is that supposed to?
That's not part of the message. That's an agreed.
Sorry, yeah.
This is the message that we just created. There it is. It's 1100 triple ones 100. You see it there.
Oh yeah. Yeah, sorry. That's my bad. That's my.
Okay.
Thanks.
Okay. So now you just need to know. Right now, this is an agreed number, so there'll be no problem, defining it. This is the frame you're going to receive, but the frame consists of 2 parts. Remember, part of it is the actual message. The actual data, I'll call it data now, but that's the message. Part of it is the actual CRC, which you must get rid of. It's not part of the message, but you need to know how many bits are there. And in this case, because we had 4-bit generator, then you should know that the last 3 bits are not really part of the data. So if there are no errors, then you should throw it away and give me just the message, right? It's part of the error detection system at the end. If it does not find any errors in the message, is to throw away the CRC and just pass the message to our user. So in our case now, we know the last 3 bits are not really part of the message. Now, so that's the first step. Now, what's the second step in the receiver? It says, do not append zeros. That's an important part, because the problem with students, sometimes they append a 0 when it's wrong. Why? Because we already have something appended. That's the CRC. It's been appended by the sender. Make sure you don't add another. So that step of appending 0 is only done by the sender. Make sure you do not do it. That's why normally we shouldn't even write it, but because many students do it and it's wrong. If you're a receiver in the question, you're told you are a receiver, then make sure you don't append zeros. Right, the next thing, you just go straight into the XOR operation. And we know right now, we should get a remainder 0. If there are no errors by the end of the division, remember the 100 are the complement of the data. So in such a way that if we divide it by that number, it should not give us any remainder. In fact, if you take a data and convert it into decimal number and see what the addition is, and if that's, you know that number, it will work on decimal as well. But for now, let's just stick to binary. Like if you work out what this decimal number is, you'll find that it will actually divide over by 7 without any remainder, if there were no errors. So let's do it. Okay, you're gonna start helping me now with the division operation. And remember, it's not division, it's XOR. So what's the first thing you do? You take that and bring it down here, 1 0 1 1, right, underneath the data. That's the, and then do the XOR. What's the first XOR? You give me the first result there. 0 1 1 1. Perfect. Right. Now I need to bring in few bits. How many bits do I bring? 1 or 2?
1.
1. Right. Now, next. You're next. I'm bringing this now. 1 0 1 1. What's the XOR here?
0, 1, 0, 0.
Perfect. And then we get rid of this 0 on the left. How many bits do I need to bring down? 1 bit, right? Now, what's the next one? 1, 0, 1, 1. What's the result there? XORing that.
0, 0, 1,
0,
0.
0, 1, 0. Perfect. I get rid of those 2 bits. Now bring down the next 2 ones. And now bring down the next one is 1, 0, 1, 1. Who's next?
0, 0, 0, 0.
Good. Get rid of all these zeros on the left and bring down the 4 bits. There are only 2 bits, and both of them are zeros, and we're finished. Right? Okay, it's finished. It's unfortunate, but you know, that's the way it is. So now, when you finish, you look at that remainder at the end and see what the receiver says here. If the remainder is not 0, does not equal 0, in this case it equals 0, but if it wasn't a 0, then there is a definite error. If the remainder equals 0, then don't say there is no error, because there is a possibility of 0.0001 of, maybe there might be an error, but it's very unlikely. We'll look into details, but it's most likely no error. If you say there is no error, you don't get 10 out of 10 in the question, you get 9 out of 10, right? But if you say most likely or something to that effect, that hey, there's a highly probable error, that if there's no error, I'll accept it. So that's how the receiver works out whether there is an error or not. This CRC is so fast, it happens so quick. It's an XOR operation. It's one of the fastest operations. Plus, the other good thing about a frame of 2,000 or 4,000 bytes, that the CRC, the sender, starts doing the calculation. It doesn't, this is one of the algorithms that you don't have to wait till the sender finishes and get the result. The moment you start at the start, you're not going to change nothing in the frame. You're just calculating. Now the transmitter can start transmitting while the sender is calculating. And by the time that the receiver, the sender finishes calculating, whatever is left, leave it there in memory, will be sent. That's there. So it's not just fast. You don't have to, the sender doesn't have to wait for the sender to do all the calculation. You can actually start physically transmitting as soon as you've gone past a few bytes. So even though it takes short time, but even that short time, you don't have, the transmitter doesn't have to wait for it. So it's one of the fastest ways to transmit. Now, let's see, I'm going to flip one of these bits, guys, and see if you can discover if there's an error in this. Right, it's the same data. I'm just going to change one small bit or 2, but I'm going to just change 1. And the good thing about CRC, it will discover everything. So the question is like this. You are a receiver. The sender sent you this frame. You've just received this following frame after CRC was carried out. So the frame is 1101 1111 00. And the generator used was 1011. Does this message contain a frame? Oh, contain an error? Yeah, you have to calculate it. Okay, use CRC now to calculate this. Provided, I told you, CRC was used to generate. And if there is no error, please give me the message. Where is the original message? Remember, okay, I'll wait till you finish. So just follow the 4 steps for the receiver. Here are the 4 steps on the screen. Identify your data, your generator, and your frame check sequence. Do not append zeros. If you've already appended zeros, then and do the XORing. find out what the remainder is. And if the remainder is not 0, then there is an error. If it's 0, is there an error? What's the remainder you got?
0, 1, 0.
Okay. Same? Okay, let me do it and prove you wrong. Identify the data and the generator. That's the generator. That's my data. But where's the CRC? I know it's the last 3 bits are CRC. So that's my data. So if there's no error, that will be the actual user message. I'll take it and give it to you if there was no error. Now, do not append zeros. Okay, I'm not appending. Start the division or the XORing. So I'm going to start 1, 0, 1, 1. You don't have to help me here. I'll do it myself, but watch me if I make mistakes. So it's 0, 1, 1, 0. Get rid of this 0. Bring down 1 bit because I only need 4 bits. So 1, 0, 1, 1. And it's 0, 1, 1, 0. Get rid of this. Now bring down the next one. And it's another, it's going to continue like this. So it's 1, 0, 1, 1. And that's 0, 1, 0. No, so that's 1, 0. 11, 1, 1, 0. I bring down the next one. And it's 1, 0, 1, 1. And it's again, same thing. So it's 0, 1, 1, 0. Bring down the next one. And it's 1, 0, 1, 1. And it's also again 1, 1, 0. Bring down a 0, 1, 0, 1, 1, and that's biggest 1, 1, 1. Bring down the next 0, and it's 1, 0, 1, 1, and 1, 0, 1. No more. Okay. The remainder is 1, 0, 1. Now, it says here, if the remainder is not 0, well, then there is an error, definite error. In this case here, there is an error. It doesn't tell you which bit, but it actually discovers the errors. In fact, CRC is so accurate that it will discover any error. There are 3 types of errors that it will discover at different percentages. It will discover any number if the error, what errors it discovers, what kind of errors CRC will discover. All errors that involve an odd number of bits. So if 1 bit flip or 3 or 7 or 21 or 103 or 113, it will discover them at a rate of 100%. It will discover all errors that involve any number of odd bits. Also, it will discover errors that are less than the length of the generator at a rate of 100%. Remember, the generator is usually 14 or 16 bits. So if it's 16 bits, then we'll discover any errors of 1 bit or 2 bits or 3 or 4 or 6 up until, as long as it's less than the length of the generator, to discover it 100%. What's left? It's left if the number of errors is even and it's greater than the generator. So errors that are even, that involve even bits and longer than the generator. It will discover them at 99.9%. So if the errors are, say, 22 or 42 bits, it will discover it at a rate of 99.9%. Now, of course, you know, many years ago, this system has been around since the 70s. And a lot of research was done on it. And they found some numbers, some generators, actually are better than others at discovering errors. So after a lot of research, they came up with those numbers, and they are actually now in the standards. You know, this is whatever standard they say, hey, this is the actual a good generator. So use this or this. They only had about 3 or 4 numbers, use any of them. And it's up to the network to pick what generator it needs. And once it uses it, it tells all its members, here's our generator. So they all use the same number. It's not a secretive number. It's not kind of key or secret, or it's known. But because the actual generators, they can be 16-bit number, they can involve lots of ones and zeros. People make mistakes when they write them. So what they decided, the people who make the protocol, and they started coming out with the generators, of course, they did not come up and give you the generator in binary. That would be too simple, isn't it? Too easy. So they came up with another way to give you the actual generator, to give programmers and users the generator. So instead of giving them in binary, they give it in something called polynomial format. So they give it in polynomial format. So what does a polynomial format? And in fact, now, if you read the protocol, they'll give you the number in some format like this: x to the power of 4 plus x squared plus 1. That's your generator. And you have to convert that into numbers, because if I give you 1, 1, 1, 1, you might mistake 7 ones for 6 ones, or vice versa, or 12 zeros, and you put only 11 zeros. So they write it this way. And now in the exam and in the books, you will also be given the polynomial generator like this. So your first step is to convert that number into binary and then perform the operation. So how do you actually convert this number? So simple. You look at these powers. You start with the first power. You say, right, x to the power of 4, that's given. So it's 1. They only give you the ones. They don't give you the zeros. So what about x to the power of 3? It's not mentioned here. That means it's a 0. X to the power of 2 is given, so it's 1. What about x to the power of 1? It's not written, so it's a 0. Finally, this one represents the x to the power of 0, so it's written. Okay, so if the power is given, replace it with 1. If it's not given, replace it with a 0. Right? So simple. So you tell me this. What do you think this number is in binary? What?
1 at the end. x4, x3, x2, x1, and 1.
Okay, so that's x to the power of 5. This is x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, and that 1 is always there as x to the power of 0. So it's so simple, right? Let's have another example. X to the power of, and it's always something else. It must start with 1 and end with 1. You can never start a generator with a 0 or end it with a 0. That's a condition for it. It has 2 conditions, actually, a generator to be used. It must start with 1 and end with 1, and it has to be smaller than the message, or else it will not work. So the message has to be longer than this generator. Right. Right, x to the power of 6 plus x plus 1. What's that number, please, in binary?
1, 0, 0, 0, 0, 1, 1.
Yeah, okay, so what about this? X to the power of 1 plus x squared plus 1.
0.
Okay. Oh, what is all right? Okay. Yeah, okay. So that's no problem. So these are the 2 points you need to watch out for. So when you're given a question in the exam, first you're told, are you a sender or a receiver? There's a slight difference between them. If you're a sender, you're given the data and the generator will be given in polynomial format. You're told to create them, the frame to be transferred. That means create the CRC. And at the end, give me the message and the CRC. Or else you're given the polynomial and you're told you're a receiver and here's the frame received. Does it contain any errors? It might and it mightn't. If there are no errors, remove the CRC and provide me just with the message. So that's CRC error detection system. Okay, you've already done this before, so this is kind of a good revision for you, I hope. But it's important that you master it. Right, last thing we need to do is called the checksum error detection system. The checksum error detection system. Remember, CRC is probably the most common and one of the best systems. It has advantages. Can you think of any advantages for CRC?
The generator is the data is smaller than the generator.
Yeah, say again?
The generator is smaller than the message.
Okay, that's the condition for it to work. But that's not I'm talking advanced. All right, that's okay if you're asked, okay, what's the condition for the generator in CRC? But now my question is, what advantage does CRC have over parity systems or over Hamming code or whatever? It finds more errors. Speed, they're all fast. Parity system is also fast. Anything that uses logical operations is extremely fast. And those three systems, they all use, logical operations. Any other advantages? Redundant data. What about redundant data? It generates very little redundant data. The remainder is always shorter than the generator, but they're always, in most networks, you send a frame and the last 2 bytes of the frame are the CRC. So the frame can be 4,000 bytes, you're only sending 2 bytes. In some networks, they use 3 bytes. That's the biggest redundant data you can send with CRCs, no more than 3 bytes. So it has very little redundant data and it discovers more errors. That's its advantages over parity and Hamming code. The advantages of Hamming code is that it can discover the actual bit, pinpoint the bit so you don't have to retransmit the message. But it has disadvantages. It doesn't always work. It only works with 1 bit errors. Let's get to the checksum. Checksum is not one of the greatest, but it's still in use today. It's used on the internet, on the TCP IP. It's used to check the error detection between end to end, but it's mostly used to check the header only. They don't use it to check the data, but this is the way it works. If you were to check a frame, you take the frame, you take the bits, let's say 1000, let me get, a few bytes, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 1, 1, 2, 3, 4, 8, and let's say 0, 0, 1, 0, 1, 2, 4, 6, 8. Let's say here's the frame. It could be many, many bytes. So what you do, the basic idea, you take that plus that, sum them up, you get something, and add it to that, and you get at the end, you get another byte, another result. Same idea. This is the first idea I gave. You add them all up and give a complement. What would add up to bring everything to 1111 or 000, and that will be the final byte. So the receiver, if the receiver add that plus that plus that plus the next number that the sender will get zeros. So let's do it. Now, this is also extremely fast and it uses 1's complement in adding. So what does it do? It takes the first byte, 1 0 0 0 and 4 ones, plus 4 ones and 4 zeros here, the next byte. Now, this is 1's complement, guy. So 1 plus 0 is 1. 1, 1, 1. This is all ones. And 1 plus 1 is a 2. Do you know how to write 2 in binary? From left to right?
0 carry 1.
Yeah, 0 carry 1, and you put the 1 here, right? Well, if we weren't at the end, we'd carry it here, and so anyway, so this is what we carry. Now, if there is a carry 1, put it there and add it to the rest of the byte. If there isn't, don't add it. So 1 plus 1 is 2. You 0 and carry 1. That's where we carry 1. 1 plus 1 is 2. 1 plus 1 is 2. You carry 1. 1 plus 1 is 2. 1 plus 1 is 2. 2. 2. 1 plus 0 is 1. And that's it. Okay, so that's the first byte. That's what we get from adding those two. Now let's add the next byte. That's another data, piece of data. So it's 0 0 1 0 1 1 0 0. Add them together. Okay, do you want to give me the results? No. 0 0 0 plus 1. You've fallen asleep, are you? Or you? That's it. There's nothing carried, and therefore you don't have to add any more. Now, that's what we get. What we need to do is we need the complement of this. So that's flip all bits. So the 0, turn it into 1 1 0 0 1 0 1 0. And that's the result that goes out with the end of that frame. Okay? So this is done by the sender. So it's simple. You add the first byte to the second byte using 1's complement. If there is a carryover, if there is an overflow, they call this an overflow. If it goes past the byte, you add it to the byte and carry on with the next one. If there is no overflow, just stop and add the next byte. When you reach the very end, you complement it. Every bit is flipped into the opposite, and that's what is appended to the end of that frame. So now I'm going to and send it. So now the receiver, what does the receiver do? First, let's see what does the sender send. So the sender sends this frame 1 0 0 0, 4 ones, and 4 ones and 4 zeros. That's byte number 2. Byte number 3 is 0 0 1 0 0 0 0. Right? 1 1 0 0. Now, and the last byte, the check byte that's sent at the end. That's the checksum byte. It's 0 1 0 1 0 0 1 1. So that's now the new frame that's sent. Sorry. That's the same frame. The bytes are the same. It's just the last byte that was appended by the sender. Now, let's see what the receiver does. Starts adding this plus that, plus that, plus that. They should all be zeros at the end. They turn into ones, ones, ones because we're complementing. Remember, we had the sum before, this sum, and we complemented it. If you actually add that to its complement, you'll find 1 1 1 1 1. If we get 1 1 1 1, that means we're okay. You know, that's what the sum should be. Anything that you complement it, you'll get the ones. Okay, so I'm going to do the same addition. So it's exactly the same, but we'll do it one more time just for fun. 1 1 1 1. Who's going to help me? Okay, you do the first two. I'm going to start at the right here, yeah? 1 plus 0?
1 1 1 1
we append that, right? So we put that plus here and do again. Go on.
0, 0, 0, very 1, 0, very 1.
That's, hold on, that's 3 here, 4 here, and 5, 6, 1, 2, 3, 4, 5, 6,
Yeah, 1 more. 0,
7, 1, and that's it. Okay, so that's that plus that. We finished with this. Now let's add this one. So it's plus 0, 0, 1, 0, 1, 1, 0, 0.
0, 0, 1, 1, 0, 1, 0.
There's no overflow, then we don't carry it, right? Then now we add the complement. Do you want to help me there? Let me first put 0, 1, 0, 1, 0, 0, 1, 1.
All ones.
Okay.
Oh, sorry.
Yeah. Oh, can't stop him, this guy.
Too quick. All ones.
1? Oh, all ones. Now, flip the last byte. This is flipping is good just to do. 0, 0, 0, 0, 0, 0, 0, 0. And if we get that, if we get all zeros, be careful, don't say there's no errors, but most likely there are no errors. If you get anything other than zeros, then there's definite error. That's the checksum. Okay. I think we probably had too much to digest tonight, but okay, it's pity we didn't record that first part, but yeah, I'll find some recording and hopefully include it on your page.
So I'm just trying to think, when would you get an error? Like, as in, you know the way it's all the same?
Okay, let's flip one of the bits and do it. That's a nice exercise before you go home, right?
No.
Get any of these bits off. Let's say at the start, say one of the bits, one of those 4 bits here. Go on, if you flip this bit into a 0.
Oh, like, oh, well then, yeah, sorry.
Then you know.
Yeah, no, that makes sense, sorry. That's what I was trying to think.
Okay.
Yeah.
So if we do that, then that one, but this one is going to be a 0. Yeah. And then if you carry on from there, it's.
I get you, yeah, that's fine.
Yeah, it's you're gonna get one of these bits changing. Okay, we're gonna let you go home early tonight. I'm sorry, my apologies, guys. Let's close this. Yeah.